Welcome to my microwave class. Hi guys! Today's scattering matrix S is being introduced. To start, we explain why a new matrix representation is specifically required for microwaves. Then, we present the origin and usefulness of this new representation. Afterwards, we illustrate some similarities with the transmission line theory. Then we will establish a generalization formulation of the scattering matrices application to encompass any load or generator's internal impedance. Finally, because all matrix representations Z, Y, H, G, or ABCD are still useful, it's necessary to have a mean to go back and forth from one representation to another. As an example, we'll build an expression to convert an impedance matrix Z to a scattering matrix S. Let's start by enumerating the limits of previous matrix representations. In circuit theory, we often use matrix representations to characterize an electrical network. You are certainly familiar with finding the Z, Y, G, H, or ABCD matrices for some basic circuits. To measure or calculate the elements of those matrices, we use either short circuits or open circuits. For instance, with the impedance matrix, we write two dependent variables, namely the voltages V1 and V2, in terms of independent variables, namely the currents I1 and I2. That is, V1 equals Z11 I1 plus Z12 I2, and V2 equals Z21 I1 plus Z22 I2. And this expression is readily written in matrix form. To determine Z11 and Z21, we let port 2 open, leading to I2 equals 0, and after measuring the voltage and current on each port, we get the desired elements. Z1 equals V1 on I1 when I2 equals 0, and Z21 equals V2 over I1 when I2 equals 0. Then we let port 1 open, forcing I1 to 0, and measure again the voltage and current on each port in order to calculate the remaining Z matrix elements. We get Z12 equals V1 over I2 when I1 equals 0, and Z22 equals V2 over I2 when I1 equals 0. At low frequencies, nothing prevents us from using an open circuit or short circuit as a terminal load, although high currents may arise from the latter. However, at high frequencies, both short circuits and open circuits are prohibited because of the significant VSWR they generate. Also, as frequency increases, these components are difficult to build because an open circuit will gain a parasitic capacity while a short circuit will acquire a parasitic inductance. Aside terminal loads, it's important to note that high-frequency ammeters and voltmeters are not commonly used microwave devices because of their limited frequency range, making it impossible to measure the voltages and currents involved in the computation of the elements of the impedance matrix. Moreover, loading active devices with highly reflective loads, such as short circuits and open circuits, leads to unpredictable results. For example, a stable amplifier may turn to an oscillator. Finally, it's worth emphasizing that some matrix representations fail in modeling some basic circuits. Here is an example of a basic quadrupole that doesn't have a definite impedance matrix. Now we will build a new matrix representation which overcomes the limits of the previous ones. In the absence of devices for measuring high-frequency currents and voltages, what other measurement options do we have, and what types of load can replace open circuits and short circuits? From the old days of microwaves, it has always been possible to measure average relative power because the primary focus in this particular industry is the transmission of power. One could use either Schottky diodes or thermistors for these measurements. We also excel in measuring phase shifts thanks to phase detectors and PLLs. Consequently, the new matrix representation will be based on the measure of power and phase. Thus, this new tool will be highly beneficial for obtaining information on power transfer. In particular, it will primarily answer the following question. If a generator of internal impedance Zg is connected to a load ZL, what is the ratio of power consumed by ZL compared to the maximum power the generator can provide? From circuit theory, we already know that the maximum power a generator can provide is called the available power and is reachable under the conjugate matching condition, which states that ZL must be the conjugate of Zg. In this condition, the available power PA equals the square of the magnitude of the EMF of the generator Eg over 4 times the real part of the internal impedance of the generator Zg. But when the conjugate matching condition is not satisfied, the power consumed by the load PL will be less than the available power. Because microwave power is precious, we always want to maximize the ratio PL over PA. Power considerations aside, phase plays also a crucial role. To illustrate, let's say we wish to combine two signals to obtain a more significant power source. If the primary sources are out of phase, then our project is ruined, as the result will be null. Having highlighted the significance of phase and power, we face constructing a unique tool that integrates both power and phase. Since the phase signifies the delay in power propagation, our suggestion is to introduce a wave function that represents a power value when raised to square. The wave will be called the A wave, and it is identified by magnitude and phase. As any type of wave, we can imagine that this particular wave could be either incident or reflected. For instance, with the following figure, we assume the generator sends all its available power to the load, but because the latter is not conjugate matched, then it will not absorb the total incident power. As a result, a portion of that power will be returned to the generator. The wave transporting this backward power will be called the B wave. The B wave will also be identified by its magnitude and phase. Let's explain it again. The generator creates an available power PA. This power is transported by an A wave to the load so that PA equals the square of the magnitude of A. As the load is not able to absorb such a power because of its mismatch, it will consume only a portion PL. As a result, a reflected power PR will be transported by a B wave so that PR equals the square of the magnitude of B. The power budget is then clear. PA equals PL plus PR. Or in terms of waves, the square of the magnitude of A equals PL plus the square of the magnitude of B. Knowing the expression of PA, which is the square of the magnitude of A, and PL, it is possible to find an expression of PR, which is the square of the magnitude of B. The details of the calculus are given hereafter. We find that the square of the magnitude of B equals the square of the magnitude of A multiplied by a power reflection coefficient. This power reflection coefficient is the square of the magnitude of gamma L, where gamma L equals ZL minus the conjugate of Zg over ZL plus Zg. Let's now write the A wave in terms of the voltage and current across the dipole. We simply replace Eg by VL plus ZgIg. We find that the square of the magnitude of A equals the square of the magnitude of VL plus ZgIL divided by 4 times real part of Zg. If we choose the A wave as the phase reference, then we can simply write A equals VL plus ZgIL over 2 times the square root of the real part of Zg. For the B wave, we know that the square of the magnitude of B equals the square of magnitude of A dot the square of the magnitude of gamma L. Thus, the magnitude of B equals the magnitude of A multiplied by the magnitude of gamma L. The phase of the reflected wave can be determined by adding together the phase of the incident wave with the phase of the reflection coefficient, which represents the time or delay required by the dipole to restore power to the network. Consequently, we express the relationship between the B wave and the A wave as follows: B equals A dot gamma L. Then it's easy to find the expression of B. We know that B equals A multiplied by ZL minus conjugate of ZG over ZL plus ZG. Then we replace the expression of A. Then ZL is substituted by VL over IL. And finally, we get B equals VL minus conjugate ZG dot IL over 2 times square root of the real part of ZG. Finally, we recall hereafter the waves and reflection coefficient expressions. In the scattering matrix representation paradigm, backward waves are written in terms of incident waves. With a dipole, we have only one incident wave and one backward wave, and the matrix is reduced to a scalar, and we write B equals gamma L dot A. Here, the independent variable is the incident wave, and the dependent variable is the backward wave. Unlike previous matrix representations, the dependent or independent variables are neither currents nor voltages, but are rather a linear combination of them. Furthermore, we notice that dependent and independent variables definitions rely on the use of the internal impedance of the generator. The spatial impedance will be called the reference impedance in the paradigm of the scattering matrix. It's time to generalize the dipole formalism to a two-port network. Since the latter has 2 ports, then we will handle 2 A waves, namely A1 and A2, and 2 B waves, namely B1 and B2. We will also have one generator on each port with different internal impedance Z1 and Z2. Thus, our scattering matrix will have one reference impedance on each port. We express the backward waves in terms of incident waves and get B1 equals S11A1 plus S12A2, B2 equals S21A1 plus S22A2. We write this set equations in matrix formalism, so we get B equals S by A. The expressions of the E waves and B waves are given hereafter. As with all previous matrix representations, it is possible to measure or calculate the elements of the S matrix. We get S11 equals B1 over A1 when A2 equals 0, S21 equals B2 over A1 when A2 equals 0, and so on. But how can we enforce the condition A1 equals 0 or A2 equals 0? In general, to enforce AI on port I to 0, it suffices to switch off the generator EI and close the port I on its reference impedance ZI. Indeed, in these conditions, we have VI equals minus ZI dot II, leading to AI equals 0. The following figures illustrate calculating or measuring the elements of the scattering matrix. First, we close port 2 with Z2 and evaluate the ratio B1 over A1 to get S11. We also evaluate the ratio B2 over A1 to evaluate S21. Then we close port 1 with impedance Z1 and evaluate the ratio B2 over A2 to get S22. We also evaluate the ratio B1 over A2 to evaluate S12. The device known as the Vector Network Analyzer, VNA, is particularly effective in measuring the power ratio between incident and backward waves. Furthermore, it has the ability to precisely determine the phase between them, thereby yielding the values of the scattering matrix parameters. Let's examine each element of the S matrix in order to understand its significance. If S11 is raised to the power of 2, it will represent the power ratio of the reflected wave to the incident or available power. The parameter S11 can be written in terms of the input impedance of port 1. S11 equals B1 over A1 when A2 equals 0, which is equal to V1 minus conjugate Z1 I1 over V1 plus Z1 I1, which is equal to Zin minus Z1 conjugate over Zin plus Z1, where Zin equals V1 over I1. Ideally, the backward wave should be null, which happens when S11 equals 0, corresponding to Zin equals Z1 conjugate. In that case, all the incident power will be consumed by the port 1 of the quadrupole. If S11 is different from 0, then the quadrupole will not benefit from the generator's available power because its input impedance mismatches that of the generator. That is, Zin different from Z1 conjugate. The lost power is quantified using the reflection loss defined as follows. R equals minus 20 decimal logarithm of the magnitude of S11. For S21, let's consider again the case where port 2 is closed on its reference impedance Z2. Raising to square S21 gives the square of the magnitude of S21 equals the square of the magnitude of B2 over the square of the magnitude of A1 when A2 equals 0. The power consumed by Z2 is P2, so as P2 equals the square of the magnitude of B2 minus the square of magnitude of A2. But because A2 equals 0, then P2 equals the square of the magnitude of B2. Thus, the squared value of the magnitude of S21 represents the ratio of the power consumed by Z2 to the available power. Therefore, S21 gives information on whether the quadrupole is amplifying or attenuating power. If the magnitude of S21 is greater than 1, then we talk about power transducer gain GT. The power transducer gain GT is 20, the decimal logarithm of the magnitude of S21. But if the magnitude of S21 is less than 1, then we rather consider the insertion loss I defined as follows. I equals minus 20 times the decimal logarithm of the magnitude of S21. It's time to establish a relationship between the scattering matrix and transmission line theory. The transmission line theory states that at any point x of the line, the voltage is the superposition of an incident and a reflected wave. We write V equal V incident plus V reflected. The same rule applies to the current. That is, I equals I incident plus I reflected. We also know that the incident and reflected waves are related as follows. Incident current equals incident voltage over Zc, and reflected current equals minus reflected voltage over Zc, where Zc is the characteristic impedance of the line. Assuming that the reference impedances are chosen identical to the line characteristic impedance, let's replace all these quantities in the expression of the A wave. We get A equals the incident voltage over the square root of the real part of the characteristic impedance of the line. Our conclusion is that the A wave and the incident voltage wave are directly proportional. Likewise, the B wave is anticipated to have a proportional relationship with the reflected voltage wave. Let's check. After some development, we notice that we cannot have further simplifications because Zc is not necessarily real. However, if the characteristic impedance Zc is real, then we get B equals the reflected voltage wave over the square root of the real part of the characteristic impedance of the line. In these conditions, the B wave and the reflected voltage wave are directly proportional. Let's try to find the scattering matrix of a quadrupole by analyzing its topology. The depicted figure shows the example that is being discussed. For this example, we choose a real reference impedance Z0 on both ports. Therefore, we use generators with internal impedance equal to Z0. In order to evaluate S11 and S21, we enforce A2 equals 0 by switching off generator E2. Then, we use elementary circuit theory to obtain the desired parameters. Starting from the definition of S11, we get S11 equals Zin minus Z0 over Zin plus Z0, where Zin is the input impedance of port 1, Zin equals V1 over I1, which is equal to 11 over 15 Z0. Thus, S11 equals minus 2 over 13. Similarly, for S21, we find S21 equals V2 minus Z0 I2 over V1 plus Z0 I1. But as V2 equals minus Z0 I2, then S21 equals 2V2 over V1 times the sum of 1 plus Z0 over Zin, where Z0 over Zin equals 15 over 11, and V2 over V1 equals 3 over 11. Thus, S21 equals 3 over 13. Now, to find S22 and S12, we enforce A1 equals 0 by switching off generator E1. Then, we use again elementary circuit theory to obtain the desired parameters. Once again, we start with definition of S22. We find S22 equals Zout minus Z0 over Zout plus Z0, where Zout is the output impedance of port 2. Zout equals V2 over I2 equals 15 over 11 Z0. Hence, S22 equals 2 over 13. Finally, we get S12. S12 equals V1 minus Z0 I1 over V2 plus Z0 I2. But as V1 equals minus Z0 I1, then S12 equals 2V1 over V2 times the sum of 1 plus Z0 over Zout, where Z0 over Zout equals 11 over 15, and V1 over V2 equals 1 over 5. Thus, S12 equals 3 over 13. We notice that S21 equals S12. This result does not pertain specifically to our problem. In fact, it is a consequence of the reciprocity theorem. Finally, the network has the following scattering matrix. Now that the matrix has been found, what can it be used for? Conducting a power budget is a straightforward task. If the generator E1 has an available power of 1 watt, and assuming that the generator E2 is switched off, then the input port of the network will reflect PR1, such as PR1 equals the square of the magnitude of B1, which is equal to 0.024 watt. The power reaching the network port 1 will be P in 1. P in 1 equals PA minus PR1, which is equal to 0.976 watt. The power that exits the network port 2 is P out equals the square of the magnitude of B2, which is equal to 0.053 watt. It corresponds also to the power consumed by the load Z0 connected on port 2. We can readily compute the power consumed by the network PD. PD equals P in 1 minus P out, which is equal to 0.923 watt. Consider the two-port network discussed earlier. Altering the impedance of both the internal generator and the load will cause the loss of significance of the scattering matrix parameters. For instance, as the generator's internal impedance changes, say Z1 equals to Z0, the available power will change. Also, as the load impedance changes, for example, Z2 equals 3Z0, the power it will consume will change. The input impedance of the network will also be affected. Consequently, the circuit will exhibit altered S11 and S21 because of the modifications in the reference impedance values on each device port. Here, we must find a new scattering matrix S prime, which must be determined considering the new reference impedances. Since we already have the circuit's topology, we can easily analyze the circuit in its new setting to determine the corresponding scattering matrix parameters. This will give us the updated insertion loss and transducer gain. This is possible because we know how our network is built. In this scenario, here is the new scattering matrix named S prime, and the detailed calculus are provided hereafter. Now suppose that we buy a device for which the manufacturer provides the measured scattering matrix S referenced to impedances Z1 and Z2. If we use those impedances as the generator's internal impedance and as the load respectively, then the provided scattering matrix parameters will give significant information about power transfer. However, if we plan to use this device with another load impedance Z'2, or we use a generator with a different internal impedance Z'1, then the provided scattering matrix parameters are no more helpful. And here again, we must determine a new scattering matrix S', which will take in consideration the new reference impedances. However, in this case, we do not have any information about the internal circuitry. So how can we find the new scattering matrix S'? How it relates to the old scattering matrix S? This problem is commonly referred to as the scattering matrix conversion. Before we tackle this problem, let's discuss some intricacies of the scattering matrix. In the following picture, the cascade connection of two quadruples is illustrated. The first quadruple scattering matrix is referenced to Z1 and Z2, whereas the second quadruple scattering matrix is referenced to Z3 and Z4. The continuity of currents and voltages is straightforward. We get V2 equals V3 and I2 equals minus I3. For power waves, we would like to have A2 equals B3 and B2 equals A3. Let's discover if it's really the case. We have just to express the waves in terms of currents and voltages, then apply currents and voltage continuity. We get new expressions of A3 and B3. By comparing the expressions of A3 and B2 as well as B3 and A2, we can conclude that these waves are distinct unless we choose Z2 equals the conjugate of Z3. Thus, in order to guarantee power waves continuity, adjacent reference impedances must be conjugated. In particular, if a dipole of impedance ZL and reference impedance Z0 is connected to the kth part of a network whose reference impedance is Zk, we can write the generated reflection coefficient as follows: gamma L equals ZL minus conjugate of Z0 over ZL plus Z0. But as Z0 equals the conjugate of Zk, then gamma L equals ZL minus Zk over ZL plus Zk conjugate. Thanks to the previous expression, we can express the conjugate matching conditions in terms of reflection coefficient rather than impedances. In this scenario, it's easy to show that Z out equals conjugate of ZL is equivalent to gamma out equals the conjugate of gamma L, where gamma out equals Z out minus conjugate of Zk over Z out plus Zk. Now let's go further and show how to get the new scattering matrix when altering the reference impedance of only one port. Initially, we have a quadrupole whose port 1 is connected to a generator of internal impedance Z1 and port 2 is loaded by Z2. We suppose the scattering matrix S is known in these conditions. Now, replace Z2 by ZL and we would like to find the new S'11 and S'21. In this situation, the A2 wave is no more equal to 0. Assuming that the condition of interconnection is fulfilled, then we write BL equals gamma L dot AL, which is then written as follows: A2 equals gamma L dot B2, where gamma L equals ZL minus Z2 over ZL plus conjugate of Z2. In order to find S'11 and S'21, we consider a new figure using the new reference impedances Z1 and ZL. In this case, we will consider new A waves and B waves that will be distinguished by the use of a prime symbol. Because port 2 is closed on the new reference impedance, we will get A'2 equals 0. Despite all these changes, there are some values that remain the same. Indeed, if we change reference impedance on a piece of paper, it won't affect the currents and voltages. Therefore, if we compare the two figures, we notice that we kept the same currents and voltages. In consequence, we can demonstrate that the condition A'2 equals 0 is equivalent to A2 equals gamma L B2. Indeed, A'2 equals 0 implies V2 equals minus ZL I2. Then we start from the definition of A2. Then we replace V2 by minus ZL I2. Afterwards, we divide and multiply by ZL plus conjugate of Z2. Here we identify the reflection coefficient gamma L. And then we replace again minus ZL I2 by V2. And we identify again the expression of the B2 wave. Now let's apply our formulas to find S'11 and try to relate it to the first scattering matrix. We have S'11 equals B'1 over A'1 when A'2 equals 0, which is equal to V'1 minus conjugate Z1 I'1 over V'1 plus Z1 I'1 when A'2 equals 0. But because voltage and currents are the same, then we get S'11 equals V1 minus conjugate Z1 I1 over V1 plus Z1 I1 when I'2 equals 0, which is equal to B1 over A1 when I'2 equals 0. But the condition A'2 equals 0 is equivalent to the condition A2 equals gamma L B2. Thus, S'11 equals B1 over A1 when A2 equals gamma L B2. In the set of equations relating backward waves to incident waves, we replace A2 by gamma L B2. We get from the second equation of the set B2 over A1 equals S21 over 1 minus S22 gamma L. When replacing the first equation of the set, we get S'11 equals B1 over A1 when A2 equals gamma L B2 equal to S11 plus S12 S21 gamma L over 1 minus S22 gamma L. So we succeeded writing S'11 in terms of the initial scattering matrix and the reflection coefficient created by the impedance ZL. Let's evaluate now S'21. By definition, S'21 equals B'2 over A'1 when A'2 equals 0. But because currents and voltages are the same, then A'1 equals A1. After multiplying and dividing by B2, we find S'21 equals B'2 over B2 dot S21 over 1 minus S22 gamma L. From the definition of B'2 and B2, we can calculate the ratio B'2 over B2 in terms of impedances, but in the philosophy of scattering matrix, we prefer to use reflection coefficients. Thus, we are writing now this ratio solely in terms of the reflection coefficient gamma L. For this purpose, we write ZL in terms of gamma L, and we replace it in the ratio. Thus, the new scattering parameter S'21. After finding S'11 and S'21, it could be necessary to find S'12 and S'22. It's not performed in this video as it involves a lot of algebraic manipulations. At this point, we would like to answer a more complicated question: what if both reference impedances change? Here, the new scattering matrix is related to the former by the use of the following formula. The new scattering matrix S' is the product of four matrices. The first matrix is the inverse of the conjugate of the matrix A. The second matrix is S minus the conjugate of the matrix gamma. The third matrix is the invert of the matrix identity minus gamma S, and the fourth matrix is the matrix A, where the matrix A is a diagonal matrix constituted of the elements AI, and the gamma matrix is also a diagonal matrix constituted by the reflection coefficient gamma I, where gamma I equals Z' I minus Zi over Z' I plus the conjugate of Zi. Here, Zi is the old reference impedance, while Zi' represents the new reference impedance. Once again, the proof of this expression relies on the constancy of currents and voltages despite changes in reference impedances. Although this relation seems complicated, we can expand it for two-port network. Starting from scattering matrix S referenced to Z1 and Z2, we would like to find the new scattering matrix S' referenced to Zs and Zl. Here are the elements of the new scattering matrix S'. Let's apply this formula to our previous example. We had a two-port network with a scattering matrix referenced to Z0 on both ports, and we got the following S matrix. Then we needed to change the reference impedance on port 1 to 2Z0 and on port 2 to 3Z0. Knowing the topology of the circuit, we got S prime. We will try to find S prime thanks to the developed formulas and without the use of the internal circuitry of the quadrupole. For instance, we will use Zs equals 2Z0 and Zl equals 3Z0 and Z1 equals Z2 equals to Z0. We calculate the reflections coefficients as well as A1 and A2. We compute the denominator, which is common to all expressions. Then replacing in each expression, we get the new S prime elements. Here they are. We end up with the same scattering matrix S prime, which has been found without any knowledge of the internal circuitry of the two-port network. The last part of this video deals with the conversion from the Z matrix to the scattering matrix. Of course, we can find in the literature ready-to-use formulas to achieve this task. Hereafter, we will show how to build these formulas. We start expressing currents and voltages in terms of power waves. From the definitions of the A wave and B wave, we get a set of two equations. Solving for V1 and I1, we get them in terms of A and B. Now we replace voltages and currents in the matrix expression. Let's define two diagonal matrices, RZ and MZ, thus decomposing the last equation as follows. Then, replacing the vector B by SA yields the following expression. Finally, we solve for S and get the desired conversion formula. If the reference impedances are real and are equal, that is Z1 equals Z2 equals Z0, then the previous expression simplifies as follows. Using the same technique, it is possible to find conversion formulas from any matrix representation to the scattering matrix. Let's try to find the scattering matrix of our two-port network through the use of its impedance matrix. First, we leave port 2 open and compute Z11 and Z21. Then, we open port 1 and compute Z22 and Z12. After, we apply the matrix formula to find the scattering matrix. From Z, we compute Z over Z0 plus identity. Then we invert the later. We also compute Z over Z0 minus identity. And finally, we compute the product. Of course, we find the same result. This ends our video, hoping you have enjoyed it. See you soon. Bye.